we discuss about depression in freezing point. The concept here is almost the same way that we discussed it for elevation in boiling point. When it comes to the definition of depression in freezing point, delta TF is defined as the temperature at which, first of all, freezing point. Freezing point is defined as the temperature at which the solid and liquid are in equilibrium. Solid, liquid, equilibrium. That is what we call freezing point. Now, in a solution or for a solution, the freezing point is the temperature at which the vapor pressure of solution becomes equal to vapor pressure of pure solvent. Vapor pressure of solution equal to vapor pressure of solvent. The freezing point is the temperature at which vapor pressure of solution becomes equal to vapor pressure of pure solvent. So, here what happens is that for a solution, the vapor pressure to become equal to vapor pressure of pure solvent means already in the vapor pressure what we told is when you add a non-volatile solute, vapor pressure increases. Solution vapor pressure is more than solvent vapor pressure. Now, solution vapor pressure has to lowered, has to decrease, has to depress to vapor pressure of the pure solvent. So, that means what you have to do is for a solution, its vapor pressure to decrease to that of pure solvent, what we have to do is we have to decrease its temperature, because with the decrease in temperature vapor pressure decreases. So, you have to decrease the temperature to whatever the temperature you have decreased the solution, so that its vapor pressure becomes equal to vapor pressure of pure solvent. The temperature is nothing but what we call freezing point of solution. For example, vapor pressure of solution. So, here what I am writing is vapor pressure of solution is more than vapor pressure of pure solvent at same temperature. Therefore, to equalize the vapor pressure of solution and solvent, the temperature of solution should be decreased. That decrease is what we call it as depression in freezing point, delta TF, right. So, in the case of water, as all of us know very well that for pure water TF naught is equal to 0 degree Celsius, that is 273 Kelvin. On adding non-volatile solute like urea or ethylene glycol, what will happen is its freezing point decreases. The decrease is what we call delta TF, depression in freezing point of water, water being the pure solvent, that is what we call delta TF. This delta TF relation to concentration again we see with respect to graph, like in the case of elevation in boiling point, with the help of a graph, the way that we explained that delta TB is proportional to molality. Same way again here we get the relation that delta TF is also proportional to molality. Delta TF is also proportional to molality, that in the graph we see now. The way in which we discussed about the elevation in boiling point for a solution compared to that of a pure solvent. In the similar fashion, graphically also we can explain the depression in freezing point for a solution compared to that of pure solvent. As you can see over here, these are as usual, of course, this is a curve that is drawn for vapor pressure versus temperature for a pure solvent. This is for solution 1, this is for solution 2. Again, the solution 1 is less concentrated than the solution 2. Now, as you can see that the solvent freezing point is, this is a freezing point, TF naught is more than the solution freezing point. This is a freezing point of the pure solvent, this is a freezing point of the solution 1, this is the freezing point of the solution 2. So, as you can see from the graph that TF double dash is less than TF dash is less than TF naught. So, again mathematically if you go, the ratio of AB to AD, that is nothing but P naught minus P dash or P dash minus P naught, whatever you take, that does not make any difference, is by P naught minus P double dash is equal to TF naught minus TF dash divided by TF naught minus TF double dash. That is, change in vapor pressure for solution 1 by change in vapor pressure for solution 2 is equal to change in freezing point for solution 1 by change in freezing point for solution 2. So, this in turn is again that decrease in vapor pressure is proportional to change in its vapor pressure from solvent to solution. And as in the case of elevation in boiling point, for the similar kind of relation, we wrote that delta TB is proportional to molality there. So, exactly again the same thing. Now, we can write that delta TF is proportional to molality, delta TF is equal to Kf into molality. In the case of elevation in boiling point, we wrote the equation as delta TF is equal to delta TB is equal to Kb into molality. Now, we are writing for the freezing point depression as delta TF is equal to Kf into molality. Now, what we can call this Kf? Kf is molal depression constant. For boiling point we called it as molal elevation, because there it is elevated, now it is decreased, depressed. So, we call it as molal depression constant or cryoscopic constant. Cryoscopy means lower temperature. Any study that we make at lower temperature is what we call cryoscopic study. Now, this is being decreased in temperature. So, we call this more specifically as cryoscopic constant. About this cryoscopic constant and its applications of depression and freezing point, now we discuss. Now, so depression and freezing point, delta TF is equal to Kf into molality, where Kf is what we are calling it as molal depression constant or cryoscopic constant. The unit for this is again Kelvin kg per mole is the unit, and this Kf is equal to RTF square by 1000 LF. this again expression is exactly similar to what we wrote for Kb in the case of boiling points, where Tf is freezing point of pure solvent, Lf is latent heat of vaporization, and of course R is gas constant. And this in turn again RTF square into m by 1000 delta HF, where delta HF is enthalpy of vaporization, enthalpy latent heat of this is not vaporization, that is vaporization in the case of boiling, this is latent heat of fusion, and similarly here it is enthalpy of fusion delta HF, and this m is molecular weight of, this is molecular weight of solvent. If it is water, the molecular weight is 18, that all if you substitute you will get K for pure water is 1.86 Kelvin kg per mole. Now, like we discussed on some simple applications for elevation in boiling point in the pressure cooker case. Where do we use this depression in freezing point? The depression in freezing point case we use especially in the cold atmosphere, cold countries, cold regions. As in the morning, everyday morning, there will be a lot of ice that gets accumulated on the roads. In the US nowadays especially, we are getting a regular news that lot of ice is getting dumped because of the freezing, very low temperatures. It will block the road traffic and all. And even in our country sometimes we see in the Kashmir and Himachal regions where there is whenever there is a snowfall. Due to snowfall, the roads will get blocked, transport is completely blocked. As a result, day to day activity gets disturbed. So is the reason that in those areas, for easy melting of that snow, in the morning loads of salts will be distributed and will be poured on that snow, so that the freezing point of that snow will get decreased and your snow will get melt easily into water. So the water will get easily drained up and blockade can be removed. This is a very direct and simple application of depression in freezing point whenever a non-volatile solute added. So there, when you are adding a salt, loads of salt will be brought and bags will be given to the public and they are asked to just put it on the snow. So as a result, when you add salt, that is nothing but you are adding a solute, non-volatile solute. As a result, the melting point decreases, and so at that particular temperature, as freezing point is further decreased, so at that higher, now it becomes higher temperature, that snow will start melting. So this is the direct application of the depression in freezing point. And also using this, what we can determine is the amount of ice formed, also we can calculate that. While doing the numericals, we take that example and also we solve how much is the ice that will be separated out from a solution at a particular temperature. Easily we can calculate. Now after this, still we have another colligative property to discuss, that is osmotic pressure. So next we go to osmotic pressure.